In the last video, we looked at a range of forces acting on a particle. One of those forces was friction. In this video, we're going to look at friction and how we can model it. Friction is a force that opposes motion. So let's draw a basic diagram, and this is going to be now a warehouse. And I'm going to have a man pushing now a box across the floor. So this now is our particle, and this is our flat plane. So I'm going to have a force, and I'm going to say that this is going to be P newtons. So the man is standing behind the box, and he is pushing it like so. Now at the moment, we're going to say that the acceleration is going to be 0. Our resultant is 0, and this is just using Newton's second law. So 0 meters per second squared. Now if we look at this, there's no obvious force acting on the box other than this man pushing it, yet it's still not moving. We want to know why it's not moving. It's not as if someone is the other side of it with this force and they're kicking it in this direction. It's not as if I've got now a rope over here pulling it in the other direction, but for some reason it's not moving. Now the reason it's not moving is that there's frictional force opposing this motion. So what we'd have now is a frictional force, and we generally say that that is going to be F. So let's model that up, and we'll say now the frictional force is F. So the frictional force is opposing motion. Now, force P might be increased a little more, and it still doesn't move. Ultimately, P, if it becomes so strong, it will actually move. It will overcome the frictional force. Once P exceeds a certain value now, we will have a positive acceleration in this direction. Now, we call that point limiting equilibrium. So when the box is on the point of moving, friction is said to be limiting. So we have what we call the frictional max. So on here now, the frictional max, and we can write that as F max, would be at its absolute limit, and then we would get an acceleration, and we could say that acceleration was A meters per second squared. We write friction now as less or equal to mu r, where mu is the coefficient of friction and r is the normal reaction force. So let's just look at the normal reaction force. This is something that we saw in the last video. The normal reaction force is perpendicular to the plane. This essentially counteracts now the weight acting downwards, and it ensures that we don't accelerate through the floor or we don't accelerate through towards the ceiling. Now if we had a weight here, a mass of m, we'd have a weight of mg. So this is mg newtons, and this would be the normal reaction force. So what we've got is frictional force is at most now mu r. And when we have frictional max, i.e. we get movement, then we can say that this is at its limit. Now let's look at this idea of mu. Mu is the coefficient of friction. This now gives us a value between 0 and 1 in general, and that describes now the two surface areas in contact. This is independent of both mass and the surface area in contact. So say we've got let's say we've got now a surface area. Say we've got a little particle like this, and it's got a tiny mass and it's got a tiny surface area. Or we've got a large surface area and a large mass. It doesn't matter. Mu, the coefficient of friction, describes or is now simply the relationship between these two surfaces in contact. So if we had a coefficient of friction closer to 0, that might be an eel in a Teflon pan. It might be slipping all over the place. If we had a coefficient of friction closer to 1, that might be some really rough bottom boots on some really, really rough old wood. So it's really grippy. So the closer we get the coefficient of friction to 1, the better the grip. In a later video, we will look at inclined planes and the consequences of friction on an inclined plane. Many people see friction as a bad thing. Without it though, life would be an absolute nightmare. We certainly couldn't walk anywhere, and in terms of something as simple as writing, I couldn't write. My pen would simply slip off the paper all the time. So this now is F. The frictional force is at most mu r. So let's now look at this, and we'll do some modelling up of this scenario. What I'm going to do is just put on a flat plane, and we're going to take now a particle. So what I'm going to do is have a rope, and my rope is going to be pulling in this direction. And we've seen before that we can model this up, and we will call this T. Okay? Now let's say we've got T. T is going to be the tension in that rope. So let's go ahead and do that. Let's say that's T. Now we're going to have a frictional force, and I'll make these numbers quite nice to start with. We're going to have a frictional force that opposes the motion. So we can say that this is F. I'm going to now have a normal reaction force. So normal reaction force is perpendicular to a plane, and that looks something like so. So let's put that just there. And then we'll have a weight acting downwards. Weight is mass times gravity. So let's say we've got a mass now. Let's say we've got a mass of m. The weight is going to be mg. And now we're going to have now a normal reaction. In fact, let's give these some numeric values to make this even easier. Let's say that we've got now a mass of 10 kilograms. So the weight acting down will be 10 g newtons. We're going to have a normal reaction force. So let's go ahead and say now that we've got this scenario where the frictional force is going to be at most mu r. Okay, I'm going to give mu a value, and we're going to say the coefficient of friction is going to be 1/2. So this is somewhere in the middle. So it isn't your eel in a Teflon pan, and at the same time it isn't your most grippy boots on the grippiest floor. It's somewhere in between. Now let's say I've got no resultant force, I've got 0. What we could do is look at a range of values of t that would satisfy, or t would satisfy that equation. Let's just start off now with the following. Let's go ahead and say now the value of the frictional force at its most. So if we look at this then, what we can say is r, resolving upwards, we can say from here that r is going to be equal to 10g. We know Newton's second law. We can say that the normal reaction force is going to be 10g, and that's newtons. All I've done there is F is equal to ma, and I've said now that r minus 10g will be equal now to 0. If you haven't seen the last video, please do check that out now, as that will then make sense. So if we look at this frictional force then, essentially we can go up to now, we can say the frictional force will be less or equal now to 1/2 of this. So this is going to be 5g. So all I've done is taken mu and then multiplied it by r. So my frictional force at most can be 5g newtons. Let's say that now I had a tension, and let's say my tension was 2g newtons, okay? G, remember, is just 9.8 meters per second squared. Now, at the moment, we're going to have a 0 acceleration. This isn't enough. There's not enough tension to make this move. The friction is holding it. So we'd have now 0 meters per second squared. Okay, let's say I crank this up and I had 4g newtons in my rope, and I was pulling now with a 4g newton force. It still isn't going to move. Now, what we can say at this stage, we can say that the frictional force is not limiting. It's not at its max. It's not under any pressure for this to accelerate in this direction. Let's now crank up the tension to 5g newtons. At this stage, we say now, despite it not moving, it's on the point of moving. It's in limiting equilibrium. So what we can see are these two forces are equal, and we say at this stage, if t is equal to 5g, we can say that the F, the friction, is equal to mu r. It's now frictional max. We can write frictional max, and it's in limiting equilibrium. So we can say it's in limiting equilibrium on the point of moving. So limiting equilibrium, there we go. Okay, so that's the scenario. Now, as soon as I go beyond 5g newtons here, we're going to get an acceleration. And let's go ahead and do that. So let's go ahead and do that. Let's put some values on. So this is kind of me thinking out loud, and hopefully it's making some sense as we go. Let's say now that I crank up, and let's say that I do this, and we end up now with the frictional force. Now the frictional force is going to be at maximum, okay? And that maximum just here is going to be 5g. We've seen that's just the product of the normal reaction multiplied by the coefficient of friction, which I chose to be 1/2. So we've got now 10 here, and I'm going to crank this up, and I'm going to say that this is going to be 6g. If we now look at the acceleration, what we've got just here, let's go ahead, we can put this on, and we can say, let's say that this is going to be a meters per second squared. Using Newton's second law, and often we write this as NTL, Newton's second law, F is equal to ma. We saw that now in the first video. We can see F is equal to ma. So now if we resolve in the direction of motion, we're going to have the 6g minus 5g will be equal now to 10 multiplied by a. That's just mass times acceleration. So from here we can see the following. That gives me now g. G is 9.8. 9.8 is equal to 10a. Divide now by 10, so 0.98, and that's going to be a. And that's going to be the acceleration. So 0.98 meters per second squared. And that gives me an acceleration. And that means that this box, or whatever I'm pulling, the particle, is now going to move in this direction with now an acceleration of 0.98 8 meters per second squared. That's because I've overcome the frictional force. At 2G with tension, it wasn't good enough. The frictional force was too strong for me. At 4G, he was still winning, or she was still winning. At 5G, we were in tug of war. We were in limiting equilibrium. The resultant was still 0. It still wasn't moving. Then I said, do you know what? Yeah, do one. 6G, let's crank this up, let's pull it. Now, if I whack that up to 10G, all we would do is simply resolve. So let's say instead of 6G, let's go ahead and do 10G. So what I'd have now is 10G minus 5G is equal to the mass, which is 10, multiplied by some acceleration, and I'll call that B meters per second squared. Okay, so all we've got here now is 5G is equal to 10B, and dividing both sides by 10, that's going to give me 4.9, and that will be meters per second squared, and that would be the acceleration B. I've just changed it from A because we had A just here. 5 times 9.8 is 49, divided by 10, and we get that. So there we go. That's a nice example of how we can have limiting friction, or we can be in limiting equilibrium. In a later video, we will look at this now in terms of an inclined plane. But as you can probably imagine, having friction on an inclined plane, it's really quite important. I don't want to put a box somewhere up a hill and just stand there watching it roll back down or slide back down and knock me out time and time again. We need friction in life. People seem to think constantly it's a bad thing. It isn't. It certainly helps us out. If we got in our car now and there was no friction, it would be worse. It would be a million times worse. Probably not a million times worse, but far worse than trying to put a car on an ice rink. It would just be an absolute nightmare. The brakes wouldn't work. We wouldn't be able to stop if we once started. If we'd stopped, we wouldn't be able to start, and it would just be a complete nightmare. At this stage, we could go on and look at the difference between static and dynamic friction. In this particular unit, though, it's overlooked to some extent. So all we're going to do is model some basic scenarios. As you've probably seen with the other videos, a lot of these do exclude certain subtleties. But all we're doing is getting some idea on how this works. So let's go ahead and look at another example. So let's make something else up. Let's go ahead and look at something. Okay, let's say now I've got a particle. Let's say I've got a particle. So let's put the particle again on the flat plane. We're going to have the normal reaction force, weight acting down, normal reaction force will be perpendicular. So we're going to have that. And let's go ahead now and let's put now a 10 Newton force. Let's really push a boat out with our 10 Newton force. Okay, let's put now a frictional force opposing the motion, and let's go ahead and look and find out now if this is going to be limiting. Let's say that we've got now, let's give this a mass of 80. So the weight acting down is 80 G newtons. We'll have a normal reaction force. Let's say we've got now 10 newtons. Let's say I'm pulling with 10 newtons in this direction. Let's say mu, the coefficient of friction, is going to be equal to, let's go for a quarter, make my life slightly easier. Is this now in limiting equilibrium? So let's put the frictional force here. Now if we consider frictional force is at most mu r, where mu is a coefficient of friction and r is the normal reaction force. So let's go ahead and get the normal reaction force. So if we want to go the long way round, we can look at Newton's second law. R minus 80g, this is just simply resolving upwards, is going to be 0. This isn't accelerating downwards, it's not accelerating upwards, so we can say that R is equal now to 80g. Okay, let's now look then at the frictional force. So what we can say then is the frictional force will be at most 1/4 of this. Okay, that's R, that's mu. So we can say now that this is going to be 20g. So we can see now that this is going to be it's going to be staying still. It's not moving. There's no resultant force. I've got this weak 10 Newton force trying to pull against 20g. Remember, G is 9.8. It would only be now if I crank this up beyond 20g that this would start to accelerate in this direction. So if this was now a fixed point and it wasn't moving, it would no longer move until we really ramp this up. So if we were asked to find the value now of the force right here, so let's say we had to apply, let's say we got another force, let's go ahead and really push the boat out. Let's say we were asked to find now the value of let's say the value, let's call this P, let's call this force P. Often force is called P. Let's find the value of the force P that is going to now ensure that we have limiting equilibrium, and therefore we'll look at values of P that will now make this accelerate in this direction. So let's have a look at that. Let's go ahead and then we'll look at some different scenarios. So what we could say then is the following. We could say that P minus, in fact we'll add the 10 first. Let's go for P plus 10 minus now the frictional force at its maximum, which will take it to be now, let's say the frictional max. So let's say frictional max is the 20G. So we've cranked it up to its max. Minus 20G now is going to be equal to 0. Okay, that's now the point of limiting equilibrium. So what we could say is P would be equal to 20G minus 10, and that would be the force required. So if P was any greater than this right here, then we're going to have some positive acceleration in this direction, and that would be a meters per second squared. And of course we could work that out quite easily. So if we think about 20G, what's 20G? 196. So if P now was greater than 196, so let's put this in, 196 minus 10, we would say P is greater than 186, and that's newtons, remember. Then we would say that A would be a positive value, and we'd start pulling this box away, and the friction could no longer hold on. So at this point now of 186 newtons, we've got limiting equilibrium. This isn't moving, or if it is moving, it's staying at the same speed. Now, being in equilibrium doesn't necessarily mean that the thing isn't moving. It just means it's not accelerating. So a nice example, if you've got now something going around a track, and it's going around the track at a nice constant speed of 10 meters per second, that is in equilibrium. It's only when it accelerates, or if you like, decelerates if the acceleration is negative, that it's no longer in equilibrium. So the idea of being in equilibrium doesn't restrict it to being in one place, i.e. it just with a zero velocity. It just means now that it's not accelerating. Okay, let's look at another model. So I'm modelling these up as we go. Hopefully it's giving you some idea on how this works. So let's look at something slightly different. Say we've got now this particle. So particle is here, and we'll put some information on. So let's put the weight acting down. We will give this some value. Let's give the mass. What should we have for the mass? So there's normal reaction. Let's take the mass here to be, let's go for 10. Let's say we got a mass of 10, okay? So we're going to have now a mass of 10. So we're going to have a weight acting down of 10 G newtons. We'll have now a normal reaction force. So that's what we got at the moment. Let's go ahead and put some values on here. Let's say I pull in this direction. In fact, I'll change this over. Let's say I put some, push this. All right, last one I was pulling. So what we've got then, we're going to push this, and I'm going to push this with a 50 Newton force. So I'm going to get my muscles out and give that a good push. Okay, let's say we've got frictional force opposing the motion, and I'm going to put this that way around. I could put it just there. It's just in the opposite direction. So what I'm going to do is just say that the frictional force is just here. Okay, so frictional force is just here. Let's define some values. Let's choose some values. Let's say we've got an acceleration. Making the numbers quite easy, we'll say that we're going to accelerate. Let's go for 3 meters per second squared. Okay, so 3 meters per second in this direction right here. And let's say that we wanted to find mu. Okay, we were asked to find mu. Now, if we consider what we've got here, we have acceleration. So my 50 Newton force has overcome the friction right here. So let's go ahead and use Newton's second law. So firstly, what we can do is resolve upwards. We can say now that R minus 10G will be equal to 0. So the normal reaction force will be 10G newtons. Okay. Now let's look at resolving the other way, and we'll resolve in the direction of motion. So what we've got here is 50. So we've got 50 newtons minus the frictional force will be equal to the mass times the acceleration. So this is going to be 10 lots of 3. And that's just Newton's second law. F is equal to ma. Now what we say at this point right here, if we've got movement, we can say now that F is equal to mu r. And you need to refer to this in your work. You've got to say that it's at its limit. If we've got this acceleration in the positive x direction, as it were, or from left to right, then this is going to be at a maximum. And we can say F max. And you do need to state that you understand that, because it's quite clear that, you know, we're breaking now the force that's opposing it. So what I could now write is the following. I could write 50 minus this 30 will be equal to the frictional force. So 20 will be equal to the frictional force. Now we know that if this is limiting, and we'll write it here, we can say friction is limiting, we can say mu r, so 20 will be equal to mu r. So we know we've got this value of r is 10g. So we can say that 20 is equal to mu, which we need to find. We need to find the coefficient of friction, multiplied by 10g. Okay, so we could just simply divide through and say that now 20 over 10g is equal to mu. So what we've got then is now 2 over now 9.8. So that is going to be the coefficient of friction. Now if you come up to have something wild, so let's do that. My brain, let's go ahead and do 2 divided by 9.8. What's that give me? 10 over 49, 0.204. If you come up with a coefficient of friction of 8 or something stupid, quite clearly we're aiming for a number between 0 and 1 in general with this, okay? So if you don't, kind of go back and look at your workings. So what we've done is, given this has got an acceleration of 3 meters per second squared in this direction, got a 50 Newton force, the frictional force is limiting, it's at its maximum, it's trying to hold on, it can't, and then we end up now finding mu, given all the other information. So that might be a nice question that you're given. Let's look at one more. Let's have a go at something else. Let's say we had now a plane. Again, this is just a flat plane. Let's say I go ahead and model a particle. This time I'm going to do something slightly different. Let's go a force that's at an angle. So I'm going to crank up an angle right here, and I'm going to put a force on, and we'll call that P. Let's call P, okay? Let's go ahead and do this. So if we look at this, and I'm going to make this slightly more involved, what we'll have P, we'll have some frictional force, so let's put that in that direction. We'll have a normal reaction force. Now, when students are dealing with these problems, often they forget now that the normal reaction force is going to be influenced by this force P, and often they miss it out in their calculations. So let's give these some nice numbers again. Let's go ahead, let's just say mu. Let's make our working nice and easy. Mu, coefficient of friction. So remember, this now tells us about the relationship between these two surfaces. It doesn't tell us anything about now the mass. It doesn't tell us how heavy I am, you know, sliding back down a hill or sliding along here. It's just concerned with now the two surfaces in contact. Let's make our numbers easy. Let's say this is 30. Let's say that we've got now some force. And I'm going to call that force P. Let's say this is P. I'm going to put an acceleration on. So let's put an acceleration on. We'll go for something nice and easy. Let's go for 1 meter per second squared. Okay, so 1 meter per second squared. Let's give this a nice value. Let's say this is going to be 10 again. Weight acting down is 10 G newtons. Normal reaction now. Normal reaction is perpendicular to a plane. And let's say we got some frictional force. Okay, now if we consider that this is accelerating, straight away we can say frictional force is equal to mu r. We can use the word limiting. It's in limiting friction. The friction is limiting. We've now gone beyond the stage. We've now got movement in this direction. We've overcome that force. Now, as we can see here, we've got at the moment 3 unknowns. We've got the frictional force, we've got P, and we've got the normal reaction. We can solve for these by resolving essentially parallel and perpendicular to the plane, and we can find the value of P, and we can find the value of now R, the frictional force. We can find them all. So let's now look at resolving upwards. So this is going to get quite messy, and certainly you could look at doing this a couple of different ways. Let's resolve upwards. So what I've got then is R plus, now if we saw the last video, we're looking at the vertical component of this force. The vertical component of this force, and I'll just draw a quick sketch now, is going to be P sine of 30 degrees. So this is basic right angle trig, and we sort of looked at this idea before. So what we've got then is P, this is a right angle triangle, this is 30 degrees, and the hypotenuse of that now is the force P. So what we're interested now is, in terms of, if we're resolving upwards, the vertical component of this force. So when I'm yanking this rope, just how much is pulling upwards and helping now this force here. If we go back to basic trig, this is SOH, okay? We want the opposite, it's the sine of the angle multiplied by the hypotenuse. So we can say that this is going to be P sine 30. Now we've got the weight acting down, so that's going to be minus 10G. And now the resultant force is going to be 0. We're not accelerating upwards. You know, it's not as if I'm standing there watching my, my box crash through the ceiling up here. This is 0. So when we use Newton's second law, we're now 0 meters per second this way. So NTL with my workings. Okay, so from here, what we could say, now I'm going to write these here. The sine of 30 degrees is going to be 1/2, and the cosine of 30 degrees, which we will use shortly, is going to be √3/2. And these are exact values. Of course, you can use a calculator. But if we look at this now, what we could say from here is the following. We could say that either or, we could take our choice. We could say now that 1/2 p, so we could say 1/2 p, sine of 30 is half, 1/2 p will be equal to 10g minus r, okay? Multiplying through by 2, we could say p is equal to 20g minus 2r, okay? So that's what we could do. And that's one equation. So we've still got these two unknowns. Now, if we look at the other direction, we could resolve in the other direction, okay? So if we look now, we want the horizontal component of this force. The horizontal component of this force, if we consider we're looking at the adjacent here, we want how much. So when I'm pulling, how much is really helping me out this way? And that now is the adjacent of this right angle triangle. So that's simply going to be the cosine of the angle multiplied by the hypotenuse. So we can say that that's going to be P cos of 30 degrees. And then we've got now the frictional force, which is opposing the motion. Minus F will be equal to the mass, which is 10, times the acceleration, which is 1. So 10, and then we've got 1. So what I could do now is say that this is √3/2 p minus 10, if I wanted. I don't have to at this stage. I can leave it as it is. At this stage, what I can say is now minus 10 will be equal to, and I'm just looking ahead at this. In fact, we'll do it the other way around. Let's say that, I will do it this way. Let's say this is the frictional force, okay? So what we've got then is now √3/2. This is the cosine of 30 degrees. Minus 10 is equal to the frictional force. Now, I've already said that frictional force is equal to mu r because it's limiting. We've got this acceleration. Therefore, it's max. So at this stage, what I could do is write √3/2 p minus 10 is equal to mu r. Okay? So what we've got then is the following. We've got this. Now, we know that mu is 1/2, and now we can just write this in. So what we've got then is √3/2 p minus 10 is equal to 1/2 r. So if we look at this now, if I multiply through by 2, I've got √3 p minus 20 will be equal to r. So we've now got two equations. This is equation 2 and this is equation 1. So at this stage we can solve for both p and r. So if I look at this now, I've got over here, let's just write these out. Let's write equation 1. So we've got p is equal to 20g minus 2r. I've got equation 2, which is going to be √3p minus 20 is going to be equal now. So we've got now on here, minus the 20 is going to be equal to r. So at this stage now, it's entirely up to you what you want to do with this. You can sub it in right here if you want. So if we sub this in, we've got now this value. So we could say p, this is just going back into equation 1. Entirely up to you on how you want to do it. If you want to sub it in here, you're more than welcome to do so. In fact, we could probably sub this in and solve for r. It really doesn't matter. Either way around, we're going to get p and r. So p is going to be 20g minus 2, and this is r right here, which is √3p minus 20. Okay, so from that we can see now that p is equal to 20g minus 2√3p plus now 40. So just taking this over, factoring it, we got p, then we're going to have 1 plus 2√3 will be equal to 20. And we could factor it. So I've got 20g plus 40, so you could say 20 and then g plus 2. So from here, we could simply go ahead and divide. So we could say p is going to be 20. We'd have g plus 2 over now 1 plus 2√3. And of course, that gives something messy. But either or really, it's whatever's whatever at this stage. It's just simply now expressing that. And of course, if we wanted to get r, we could simply now plug it in here. And looking at that, you might want to solve r first. R might work out to be slightly better. But we simply go ahead and sub that in and solve for r. So from this, we can find these two forces, which were unknowns. So we might be asked to find the value now of p and r, given these two unknowns. So there we go, that's some work with friction, and that's about as tough as it's going to get in this particular unit when we have now this flat plane. So there we go, brief intro, and I'll let you solve for this. I'm hoping my algebra is stacked up, that looks fairly okay. But essentially what we're saying now is that we have this frictional force. Frictional force is going to oppose from motion. We can now express that as the frictional force is at most mu r, where mu is the coefficient of friction and r is the normal reaction force. Mu simply gives us a value between 0 and 1, and that now concerns the contact between the two surfaces. It doesn't look at the mass, it doesn't look at the surface area. All we would need to do then is look to see if we have limit in equilibrium. If we got any acceleration, frictional force would be a max, and we just go ahead and deal with it. I'm looking at this thinking that my algebra seems to stack up. If it doesn't, I apologise, but that is how we go ahead and solve for these two unknowns given this information. In the next video, I think we will look at inclined planes and friction on an inclined plane.